Okay. PBDEs, what are they? Why are we interested in them? 1614, that's an EPA method. Some of you may have heard about it. Some of you may have read it. Some of you may have even tried to use it. It's a starting point, but I don't think it's the be-all to end-all. Considerations on a thermotrace and DFS applications, and then a little bit on target quant. Brominated diphenyl ethers, I dare say, with all the foam in the room here today, there's probably a good likelihood that we've got brominated diphenyl ethers in here. Certainly in the computers, in your cell phones, probably more likely tetrabromobisphenol A in some of the replacements, but they are omnipresent. Because they're omnipresent, that's one of the issues in the analysis. There are 3 commercial mixtures, or 3 that were prepared. There's deca, octa, and penta. And as we'll see, octa is not really octa, but it's hepta, and maybe some hexa. Penta is mainly tetra, but it's got some penta in there as well. Deca was deca, except once you get it into the lab, you convert it into nona and maybe even a little bit of octa. So what you start with and what you end up with, you got to use the terms a little bit generally. PBDEs are banned pretty much worldwide. The hexa, or pardon me, the penta and the octa have been banned in North America. The deca was voluntarily withdrawn, so it never actually went to the point of being banned. Penta and octa have been added to the Stockholm Convention. They never added deca, but it's been withdrawn anyhow. But when they talk about commercial penta, they refer to BDEs 99 and 100, which are pentas, and BDE 47. And again, in the commercial octa, they talk about 2 hexas, 153, 154, and then the hepta 183. And there's a lot of confusion as to why 175 got in there. The common sense is that it was a coelution with 183, and they couldn't, in the early days, they couldn't tell the difference. I'm not sure it's true, but it's a good story anyhow. Yes. Commercial structure, anybody who's done PCBs will also understand PBDEs. You convert the chlorine to a bromine and you throw an oxygen in the middle. That's it in its simplest form. There are 209 congeners. You know, and certainly methods can go through and look at all 209, but typically we don't. Most of them are not present. When they made the aerochlors for PCBs, I think if you take the aerochlors, you can probably get about 150, 160 congeners that are found in all the aerochlors. When we look at the PBDEs, we're down closer to 20 to 30, and really about 8 or 10 that are common. Analytical options. You can use a number of instruments, and people do. They use what they have available, whether it's ECD, GCMS, high-res mass spec. In our lab, the only equipment we have is high-res mass spec, so that's why we run that way. There's a lot of good data being produced from ECNI, low-res mass spec. You look at fragment ions in there. Look at a 7981. You can use a low-res mass spec just like you'd use an ECD, and you're selective for the BDEs. The reality is that in many cases, ECD and MSD are perfectly good. Some of the levels we're seeing, you don't need the sensitivity that comes with the high-res mass spec. Yes, you have the absolute confirmation with the high-res mass spec, but the truth of the matter is there's a lot of good ECD data out there. You may run into some level of bromination problems, but for the major guys, there's no problems whatsoever. 1614 was the US EPA's attempt to put a method together for PBDEs. It uses 8 internal standards. I don't know, for those of you who are familiar with 1668A, B or C, it kind of takes a similar approach. It uses multiple standards in each level of bromination, and you can use those to quantify within that level of bromination. Some of the congeners have a labeled standard beneath them, some of them do not. They use a cleanup standard in there of BDE 139, and they use 2 PCB recovery standards. And this is real strange because bromine is mass 7981, PCB mass 3537. Those of you who run a high-res mass spec know that if you've got a tetrabromo with 4 times 80 in there, 320 mass units, and you've got a similar tetrachloro used as a recovery standard, just the mass separation between those and trying to get a lock mass that handles both of them just doesn't work. But that's the way it was set up. You have to remember this method was probably set up, I think in 2003 it was first introduced, and a lot of the standards just weren't available yet. In those days, BDE 209, the label 209 was not available. Calibration points, 5-point calibration between 1 and 2,000 nanograms per mil, with single point calibration for about 30 or 40 other congeners that are available. The method says use a 30-meter column. Most people have shied away from a 30-meter column. I'm going to show that it's possible, but it has its problems. Again, bromine, it's a big molecule, pure and simple. For those of us, when you've been working on the chlorinated side for so long, it's hard to really appreciate the differences between chlorine and bromine. But it is significant. They look the same, they're not. You have thermal degradation problems with BDE 209. If you get above 300, even if you're below 300, you've also got UV degradation in there. Column length is critical. Dirk gave a paper 4 years ago, on using a 6-meter column to do BDE 209. It's a great way to do it. It gets it out real nice, quick, and easy. 15-meter is pretty good. 30-meter, as I say, has its challenges. Cleanliness is next to godliness. If you thought you had background problems with PCBs, multiply that 5-fold with PBDE. It's possible, when we first started out, cleaned a set of glassware, put it down on the bench, left it overnight, came back the next morning, and found 2 nanograms of PBDE on there. Glassware has to be cleaned immediately before use. You can't leave it for even a short period of time. Typical background levels, our background levels, BDE 47. If you ever get a sample with no BDE 47 in, you've probably screwed up the analysis. It's just there everywhere. We run 20 to 50 picograms. BDE 99 and 100, somewhere between 5 and 40. In the early days, we never saw BDE 209. We said, great, we're clean. The fact is we just couldn't see it. The instrument said we could, but it wasn't. It wasn't until we put things on the DFS we finally saw it. We've got a standing background around 100. We do use a thermo DFS high-res mass spec. We run with 2 splitless GCs on there. We actually configure our high-res mass specs. Each GC has its own analysis on it. So we'll run dioxins, PCBs, PBDEs, and organochlorine pesticides between it. For the DFS, the one nice thing about the PBDEs, unlike the PCBs, if you run, I keep forgetting, in Europe you don't run 209 congeners very often, but it's a common test in North America. You have to overlapping congener groups. In the PBDEs, for the most part, for the ones we actually look at, you don't have overlapping congener groups. So you can, where you finish looking at the monos, then you can start looking at the dis, then the tris, then the tetras. You don't have to overlap your conjugate groups. Gives you better sensitivity. We use a split-splitless injection, but we use it in a pulse pressure mode. We used to run just a standard split-splitless injection. The problem is getting your deca BDE onto the column is not very effective in a split-splitless mode. People have used direct on column injection. They've gone to the shorter columns. This part that I've put in here is straight out of the thermal manual, and it explains very clearly how the pulse pressure mode runs. Essentially, you just pressurize to 40 or 50 psi for the first couple of minutes, and everything is loaded onto the column. These are parameters for a 15-meter column. Quick initial ramp of 30 degrees a minute, then a slower ramp. But the key thing is the first minute and a half of having a pressurized pulse in there. Same is true for a 30-meter column. Slightly different. You also notice that the injection temperature, we only go to between 230 and 240. You don't need high temperature in there. As a matter of fact, high temperature is detrimental to your injection. Keep it low. Deca BDE, full scan mass spectrum, off the DFS again. The one thing you'll notice is that the parent, or the molecular cluster, the dominant cluster is not the parent cluster. It's the N-BR2. This can help you a lot because the parent cluster is up around 950 mass units. But if you can take off 160 mass units, you've got a much better chance of keeping a lock mass and stability in there. Same is true for the NANA. You can take it down, further down if you want. We just run the NANA and the DECA relative to the hepta and the octa. For those of you who are also looking at brominated biphenyls, be aware that brominated biphenyl 153 and the 154 for the BDEs very nearly coalute. The problem being that a labeled bromobiphenyl 153 and the native 154 have almost identical masses. In order to resolve them on a high-res mass spec, you need 15,000 resolution. Normal BDEs run at a 5,000 resolution, so you're probably looking at a loss of 10 times sensitivity. You're better to try and resolve them chromatographically rather than by resolution. 15-meter or 30-meter column. This is an injection on a 30-meter column. Let's see, right there. There's your DECA right down there. I'll show you a better one on that. And as well, that was out in about 50 minutes. On a 30-meter column, you can get it down. Is this 30 or is it? No, it's a 15. Pat stretched it out again, 15 minutes. That's a CS1. That's these guys up here are 0.25 picograms per liter, and down here at 2.5 picograms per liter. This is between the two 30-meter column here and a 15-meter column. Again, 2.5 picograms injected on column with a pulsed purge. The method calls for a split of BDE 49 and 71. Whether you're on a 30-meter column or a 15-meter column, you can still meet the requirements of a 40% valley. I've never totally understood the reasoning for this requirement, but it is in the method. 209 breakdown. This one here, we went at 285 degrees and held it for, what is it, I can't read the 75 minutes, it finally came out. When we ramped it up to 325, in both cases you get breakdown. It's arguable that we've saved anything by keeping it at 285. We just always assume that any nana that's there was originally Deca anyhow, whether it broke down in the injector, whether it broke down on the column, or whether it broke down before it ever got to the instrument is kind of immaterial. It's all Deca originally. Some results. These were the very first samples we did about 5 or 6 years ago. And they were probably the most difficult samples I ever saw, because when we injected them, we've been used to running dioxins and PCBs, concentrate everything as far as we can. And we just got mush on the mass spec. When I said to Pat, I says, dilute them, put them up to a 1/2 mil. And he put them up to a 1/2 mil and everything was nice picket fence. That was when we first understood, these are all in ppm levels, what the potential levels were. And this is out of a Canadian river. We go the same to some lake fish a couple of years later. These are now in parts per trillion. But yes, we do get up to the low part per billion region, but a much cleaner area than what we saw before. Initially in North America, Deca was not used very much. It's now, we're starting to see more and more of it, but initially we never saw Deca. Again, I'm not so sure it wasn't from the instrument we were using back then. Greater Vancouver storm sewers. You know, lots of, we've got a control sample here that they're running from a local river, and these are out of the storm sewers. There's lots of material. I can't remember, somebody put up a new regulation. I can't even remember what it was, but you know, we're looking at total PBDEs somewhere around you know, 100 nanograms per liter coming through the storm sewer. Quantitation. I don't know whether I've got much time here. No, that's what I was afraid of. It just gets to be too much. The isotope dilution that you're allowed to use here, you can run either single standard, you can run multiple standards. The nice part about the Target Quant software, with our chlorinated PCBs, we run up to 6 standards to quantify, or 6 labeled standards to quantify. With the BDEs, we go as many as 4, and the Target Quant handles it just nicely. I think I'll stop at that.
Please leave your laptop on. So initially we wanted to have Alex at this position, but I think we are cutting too much from the lunchtime, because yesterday we had been very short with lunch. So maybe you would like to move forward and show a little bit from the Target Quant for the remaining 10 minutes as planned initially. And then we are on time with 12:30 that we move to lunch together.
Yeah, when Kyle initially asked me to speak, as he mentioned, we've been working with him on Target Quant 3, and I was hoping that to put something together on Target Quant 3, but as I understand, coming soon to a theater near you. What we're looking at here is a standard BDE analysis. We run, if we go from the bottom, in our lab we run with 4 recovery standards: a tetra, a hexa, a hepta, and a nona recovery standard. Then we've got 11 or 12 internal standards, followed by a cleanup standard. I always have problems with terminology because you know, with isotope dilution, we add the internal standards at the beginning. In many labs, for years, we've called those surrogates, but they're not surrogates. They are, in fact, internal standards and are treated as such. With the lower levels of bromination, we have one labeled standard for each level of bromination. But as we get up, we've got 2 tetras, we've got 3 pentas, we've got 3 hexas, a hepta, 2 octas, 1 nona, and 1 deca. There's our deca there. The nice thing with Target Quant is its ability to work with your different standards. If we just go in here to entries and dependencies, you can also move these things all over the place, which is handy. We know that we can set up something called an average standard. So in this case, we have a tetra average standard, which is BDE 47 and 77. We have a penta average, which has 3 standards in it, and a hexa standard, which has 3 standards in it. So in the method, when you have a labeled standard, you use that labeled standard to quantify only the analyte that it mimics. But in the case of BDE 85, for example, BDE 85 does not have a standard underneath it. So what the method says is you use the average of all other labeled standards within the group. In this case here, we have the penta average, which has 3 standards. So when we go and look at the internal standard, let's find it here. The penta average, it calculates BDE 119 and 185. When we go to the hexa average, it calculates 139, 140, and 138, which are not in there. As I say, when we use PCBs, we use up to 6 standards to average together to calculate the PCBs. More and more standards are coming all the time between CIL and Wellington. The methods will be expanded to cover more and more standards. The nice part is right now we can work with them within Target Quant. The other thing that's in here is your summation standards. The hepta levels, or pardon me, the pentas, when you look at a total penta, where are we? Right. I just did this up quickly. If we look at total deca really is the summation of 209, 208, 207, 206. You can also take in the 197. You could probably add in some of the other hexas, but you can get a calculation line right here, which will give you a result. Let's pull it up here. Where are we? Total deca. This thing grabs my window and everything's all around. But if you take that right there, you'll find out that's a summation of the ones from above. So the system is flexible. The nice thing about going to Target Quant 3 is you'll be able to do all this in a batch system where you can load in your calibration standards at the beginning, your samples, continuing calibrations. Some of you may be familiar with this type with other softwares. The speed with which it works is amazing. I've set up, it's hard to see on this because we've only got 60 or 70 compounds in here. When we, if we reintegrate this, we get rid of it and then integrate it. you know, it's momentary. I do a lot of 209 PCB congener work. We took a file of 30 PCB 209 congeners, and it took 1 minute and 45 seconds to go through it, just under 5 seconds a grouping. For those of you in the lab who, time is money, you know, we heard that yesterday from a few different people. This software definitely is a time saver for what it can do. I think I'll just leave it at that.